Good morning, everyone. So, welcome to the workshop and welcome here to organize this wonderful workshop. My name is Chen. So, today I will brief talk about some results from my group. So, basically, because some of the postdocs might not know about me, so this is my name, Chen, and before I joined the ASIAA, I was a year core fellow at the ASIAA and also an LJ. And before that, I was an IU Global Fellow at the Santa Cruz. And I got PhD from University of Minnesota. So I am being interested in broad spectrum of the computational astrophysics. And from my PhD focused on the supernova explosion, and later on to evolve some of the feedback from the supernova to the cosmological simulation, also about the first stars and first galaxy formations. So, if you're interested in this topic, please come to talk to me. And during my free time, I like to enjoy travel, and especially go to the nature. And when I come to ASIAA, I will appreciate the opportunity to be able to work at ASIAA. And also, fortunately, have a group of very bright students to work with me on various subjects. And those are some of the students, and some of them actually have been studying abroad or doing different things. And also appreciate the Director Jules also support. Please be noticed that now this year things are very hard for everyone. So the virus still not gone yet, so we still need to be careful. So this is our group website. If you want to more detail about research, we go to our website. And this year, I've been published two very interesting papers, and also been highlighted a lot in the different media. So one of these, the first one is I've been performed the first three-dimensional simulation of superluminous supernova driven by the magenta, and this is the first of this kind. And have been revealed some of the new physics during the explosion, and shed light on the understanding how some of the exotic supernova can be soft light, and how the underlying physics influence these luminosities. And this story is for Chinese for the most price. So actually using supercomputer, I've been spent millions of CPU hours running the simulation, trying to create the first 3D model of this kind of supernova models. And we evolved from a size of like a Taipei city of the nearby the neutron star to the size about the solar systems. So they require very high resolutions and physics to include to study these objects. And we really gain the new insight about these objects. Another paper being recently published on APJ is about so-called hypernova models. And this is the first hypernova model to be performed to 300 days. Before me, usually people only do that like a phase of like 30 days. And I do the 10 times larger scale on the simulation, try to review understanding about the underlying physics, especially about some of the radiation isotope, how they decay and helium the materials, and shine the luminosities. And this is a movie done by Laurent here, and showing how the evolution of the hypernova, the ejecta, and how the isotope being evolved, being decayed through all the propagating process. And from 20, 100, and 300 days, we found this radiation energy from the decay not only give out the light of the supernova, but also impact the dynamic of these ejectors. So this also been quite interesting to some of the people in the field. So this is one of the longest supernova simulation that we've done yet. So just some of the work from the students. So later I will give my stage to the student, but also before the counting of the master student here, Yes, we're working on the turbulence, how the turbulence influence the pop 3 star formation. And I think work really hard to implement bunch of very detailed physics to understanding how this multi-structured turbulence drive in the primordial gas and eventually how they trigger the star formations. And including all the relevant physics, including chemistry, zero gravity, and the spin particle validity feedback, blah, blah, blah. So this is work on progress. And the other things I want to give my stage by the Boson and also Songhan and also Sanity to brief talk about their work. So just.
Okay, so I will briefly introduce our discovery of the critical methodology of stellar mass loss. So we use the META code, which is a 1D stellar evolution code, to simulate the stellar mass loss. Mainly we do the massive star 10 to 60 solar mass. And so we find an interesting result that there's a critical methodology of mass loss. So we can see in the coordinates of stellar mass and methodology, the high methodology part they can have a large fraction of mass loss, but in the low methodology part they do not have should have very little mass loss. This is because they cannot become red supergiants. So we find that high methodology star they can evolve to red supergiant. They can have high mass loss, but low methodology star they can never evolve to red supergiant, and the mass loss is very low. And so what causes the difference is the red supergiant, just like the Betelgeuse, they have mass loss and create a very beautiful nebula. So, but the next question is, how do the red supergiant form? Why is they related to the methodicity? So we find that the answer is because of the convection instability. So there's a Ledoux criteria of the instability, and we find that here we show the radiation gradient difference. So if the difference is larger than 0, and it will be unstable. So we can see here's the peak. This peak is come from the red curve is the opacity. So this is from the iron opacity bump. And the iron opacity bump at the effective temperature 10 log T equals to 5, and this peak can cause the instability of the in the Ledoux criteria. So this will cause the instability in the shell of the star, and it can trigger the expansion of red supergiant. And we can see that in the coordinate of methodicity, in the higher methodicity part, the difference is larger than 0, and so this is the unstable part. So this is the reason of the critical methodicity. This is because of the convection instability and cause the different mass loss. Okay, so this is my part.
Good morning, everyone. Today I would like to introduce the brief galaxy merger simulation. Galaxy merger is a violent interaction between galaxies, which can be used to explain the formation of elliptical or irregular galaxy. However, humans cannot observe the entire process that takes longer than a few giga-years. So we need to model the process in a numerical simulation way. We use the hydrodynamic simulation called DINMO to model the process. All these virtual galaxies are constructed in the supercomputers, and their input parameters are based on the observation known results. And we plan to simulate the galaxies in different of properties such as size, mass, types, and so on. Our goal is to understand the outcome of the galaxy mergers by study their star formation rates and the gas properties. Our simulation can help us to understand the observation of exotic galaxies which may form after the galaxy merge. That's my talk. Thank you.
Hello everyone, my name is Song Chai. It is my pleasure to introduce my recent work, diffuse Lyman alpha emission in illustrious TNG. We start from calculating the Lyman alpha density from TNG data, and we compare with some observational results as in this figure. Here the L2 and the L3 represent the different resolution levels. The smaller number represent the higher resolution. And the collision and the recombination are the two main processes to create the Lyman alpha emission. In this plot, we can see the Lyman alpha density from TNG data is larger than the observational results. To modify this thing, we should remove some dense structure in the TNG data. Here we focus on the plate square redshift equal to 1. First thing we do is to check the contribution of different dense region. The bin size in the plot is 10 to the 0.1. We find out the recombination can dominate the contribution when the overdensity is less than 10. But in more dense region, the collision dominates the contribution. Then we set up different overdensity threshold and the sum over the Lyman alpha density. Here I also put the observational result as in this figure. Okay. Then we zoom in this plot. We can see the result from TNG data can match the observation if we set the overdensity threshold equal to 10 to the 4.5. In this project, I also try to plot a two-dimensional image of Lyman alpha radiation to see its distribution. Here the total means is the recombination plus collision. In this plot, I simply project all the particles onto the XY plane and the sum over their Lyman alpha radiation according to their XY coordinate. Then I convert it into surface brightness and the spectrum surface brightness, but I have not done some further analysis in these figures. In previous slide, I mentioned that we should remove some dense structure in the TNG data. The first thing we try is to remove all the halo members in this data, and the result is shown in this slide. The contribution of dense region become very low, and the total Lyman alpha density becomes smaller than the observational results. The next step, I will try to use several different ways to remove only the galaxy members. That's all. Thank you.
Thank you very much. That's all our results from my group, and I hope you enjoy. Thank you very much. Yeah. Which one?
Oh, okay. Sorry. First page of my slide. Thank you.
This one.
What? So, Lyman alpha emission. Yeah. It means no, here I calculated for the old data. Although you mean the observational result. The observation they use the intense mapping and remove the galaxy. Yeah, I think, and the film. Yes.
What's the question?
question? It's your time.
Sorry,
Okay.
I might have,
Please.
perhaps you mentioned it and I missed it.
Yes.
But in the case of critical metallicity for mass loss,
Yes.
is metallicity, you need opacity, is it needed at a specific radius? Or is it,
Oh, you mean the
is it a
metallic-
specific radius of the star that is important?
Oh.
Or
Yeah.
or is it in general?
Yeah, the thing is when you do a star formation with star form, there is a certain some amount of metal they sit in the molecular gas. So those are the initial metallicity. And those are always kept on the entire star. So the metallicity here is basically on the at the beginning when the star form, also on the surface, on the atmosphere of the star. Yeah, but inside, due to nuclear fusion, there are a few more and more metals, so the metallicity will become non-uniform. You get that? So,
I imagine that the important part is metallicity and opacity in the outer layers.
yes,
So
yes.
that I
This
was
on the outer layer. Yeah, but this outer layer composition is the same as the at the beginning when the star formed. Yeah.
all right. Okay, thank you.
Okay.
I'm also interested in Osan's work.
Yeah.
So the mesocle was used in your study of the metals. So it's a one-dimensional stellar evolution curve, right? So what do you expect if it's a two-dimensional or three-dimensional evolution is included? Is that any benefit or is that necessary?
For stellar evolution, what we can do is just the 1D code, because the 2D convection there will be very complex. But convection is really a 2 or 3 dimension things. So in 1 dimension they use the mixing theory like this to simplify the parameters. But this is what we can do now. But when the star have mass loss, the part of material they lose from the star, they can become CSM, and this part we are planning to do some 2D or 3D simulation.
Okay,
It's about time to move on next speaker. So, thank you. Let's thank you.
Thank you very much.